All right, it's going to be 11:15 in a second. We'll get started. So one of the questions that we just had in our 2-minute office hours before class is, what is M0? So you know how to use M0. Degree of polymerization equals molecular weight of the chain divided by M0. And so M0 is the repeat unit molecular weight. And if we put a little m or x bar n, the number average degree of polymerization, we get mn, the number average degree molecular weight. You can also formulate, if you know mw divided by m0, this equals the weight average degree of polymerization, which we don't use a lot. We generally talk about dispersity is mw over mn. And so the question is, how do you calculate m0? So we know if you see the polymer structure, there's the polymer. M0 is everything between the parentheses with the one caveat. What is the caveat for M0? What's the hard thing about figuring that out? Yes. That's right. So for addition polymerization, this is really easy. For ARB polymerization, this is really easy because you have one monomer in the repeat unit. But M0 equals molecular weight of repeat unit divided by number of monomers in repeat unit. And for step growth polymerization, like RA2 plus RB2, that's 2 monomers per repeat unit, right? AABB. AABB. That's tricky because if you don't get that right, you're not going to get M0 right to figure out X bar N correctly. So that's the one caveat. Addition, easy. ARB, easy. You just look at the chemical structure and add it up. But when there's 2 monomers in there, the M0 is different. And I think you got to practice that. That was on a homework or on a PLA. Yeah. So one of the things to review is review all the homework questions, review all the PLAs, review all the clicker questions, review the practice exam, you know, all of those things. Those are the type of questions I'm going to ask you. And like I said, there's going to be some easy ones, like this is too easy to be on an exam. Why is he doing that? And it's because I want to make sure you know the easy stuff. And then there's going to be, you know, ones that are harder that will take you 5 or 6 minutes, maybe some calculations like 2-step calculations to make sure that you can take that extra step on the question. So that's not going to be plug and chug stuff. Sometimes it will be easy or like this is easy, but I want to make sure that there's a mix of questions in terms of difficulty on the exam. I think it's going to be 20 questions. You have 70 minutes. So you know approximately how much time you should be spending per question. And remember, the written part is afterwards. The written part is going to have multi-answer questions. I'm going to ask you a couple of different things like draw the graph and give the equation. If you don't have both of those things, you won't get full credit. You'll only get partial credit. And so make sure on the written part that you answer the question I'm asking and answer all of the questions I ask you. That's really important. Don't just try and scribble something down. It won't end well, but there's plenty of partial credit on the written part. And the written part will cover the same stuff that the multiple choice exam does. It's the same material. And so that's important that, you know, things happen on a multiple choice exam. You pick the wrong answer, you know, that happens. So the written part, you know, is a place where you can really demonstrate your expertise to me by writing really nice structures, by having really nice thought out answers in the box, units, everything else, because multiple choice isn't the best way to do the exam. It's just what we have right now. And so show me how good you are on the written part. Questions? Yeah.
So will the written part be more conceptual based than rather than more?
There's going to be concept, calculation, chemistry questions, it's going to be everything. So I don't swing it towards calculations. I don't swing it towards chemical structures. I don't swing it towards concepts. It's going to be all of it in there. Yes.
How is it weighted? So the written part compared to the first one?
Well, the multiple choice part is going to be graded out of 20. So straight up, 18 out of 20. That will give you your percent. You can look it up. There's no curve in this class because there's about 10 to 15 people out there that are going to get 100%. And I think the written part is going to be about 6 points. It's shorter, and so the total exam will be 26 points graded straight up. There'll be 6 points available on the written, 20 points available on multiple choice. Because the written part is supposed to be shorter. You're supposed to turn it in 30 or 40 minutes after you do the multiple choice. Yeah, the written part's not going to take forever if you can focus and if you can just sit down and do it. Yes.
You said the written part was like a total separate section than the multiple choice. So we don't need the multiple choice open to do the rest.
No, you should, as a matter of fact, close the multiple choice, submit it, because if you run past your 70 minutes on Canvas and haven't submitted the multiple choice, it doesn't grade the stuff that you haven't answered, or you get that wrong. And so you should do the multiple choice first, submit it, then look at the written. Yeah. Because otherwise, if you lose track of time, Canvas has no mercy when that 70 minutes is up, and I'm not going to unlock it because that's not fair to everyone else. So you will only get your allotted time on the exam, even if you have to reload questions, remember, to get the things to pop up. Maybe you might have difficulty on 1 or 2 questions. But there won't be any time extensions on the multiple choice part. I promise you that. Yes.
So if we can make the multiple choice part before 70 minutes, does that give us more time?
Nope. Nope, doesn't. Yes.
Now, will we have to submit our scratch paper along with our report?
Yeah, so this is a good point. You should have your equation sheet printed out and ready. That's already posted. That's the same equation sheet that you're going to have on the exam. And if you should have some blank sheets of paper, a few blank sheets of paper to do the written part, but also blank sheets of paper to write on your scratch paper. Save that scratch paper and you can submit that the day after the exam. I want to see your scratch paper. I want to see how you're working on these problems. Of course, I can't look in the margins of the multiple choice exam because you're not going to be writing on Canvas. And so if you have issues, if you're uncertain how to do a problem, if you think there's an error, it happens. Write it on your scratch paper and submit that scratch paper. So if we have issues during the exam, or if I'm not sure about what you're doing on the exam, I will look at your scratch paper, and I want to see some healthy scratch paper writing. Yeah.
So for the multiple choice question, did we have the journal right idea, but we just get a error?
No partial credit on multiple choice. If it's wrong, it's wrong. That's why I give you the written part and the scratch paper to show me that you know what you're doing. And I'm certain your final grade in this class is not going to come down to 1 or 2 or 3 questions on the exams. There's tons of opportunities to get points. Remember, we drop an exam, but there is, as I said, no time extension and no partial credit on multiple choice. It's just unmanageable. Other questions? I'm seeing half hands. We're getting, yeah, go ahead. Sure.
So for the number average mass, it's MN equals some MJ. So which data month with MJ one?
Where is that equation? Is that in our equations for molecular weight? This one? Yeah. So this one, remember, is a copolymer M0. And so that's the molar average of all of these M zeros. So this has an M zero, vinyl chloride has an M zero, methyl methacrylate has an M zero. And so this equation is the summation of the mole fraction. So let's say if X equals 0.5, Y equals 0.1. What does Z have to equal for talking mole fraction if X is 0.5 and Y is 0.1? 0.4, because mole fraction has to equal 1. And so you need to get it in a place where the mole fraction is 1. And so this is the individual M zeros times their mole fraction, which is exactly this down here. That's different, remember, than a copolymer M0 is different than what we just talked about right here. Does that make sense? Okay, it will be clear on the exam if it's a copolymer, because so far we've just talked about how is this polymer made? What type of polymer is this? Chain growth or addition, right? Very clear what's an addition polymer versus a step growth polymer, and when you have two monomer units coming together. Yes.
On one of the PLAs, instead of doing like a percentage of each one, it said that it was like 1 to 3. How do we go about that in?
It was a ratio of 1 to 3,
Yeah,
right?
Yeah.
You just need to turn a ratio into a percentage. How do you do that? Yeah, don't forget the basics. So let's say we have, and this is why this class is tricky, because there's lots of different concepts that you need to draw on from your math classes and from everything else, right? This is an addition copolymer. It's made using styrene monomer and vinyl chloride. And so if the ratio N to M is 1 to 3, how do we change that into a mole fraction or percent? Let's just change it into a percent, and then we'll go to mole fraction. Yes.
So you can do 1 plus 3, have that be the total moles, and you do 1 divided by
Yep.
4. Yeah.
Perfect. 4 equals total moles. And so the N mole fraction is 1 over 4, and the M mole fraction is 3 over 4. These guys add up to 1. We're good. And so you can make 1 over 4 25% if you want, and then make it 0.25, et cetera, et cetera. But remember, you really want to use mole fraction. So that's tricky, right? Because I give you something that's not quite right, but based on this class, it's a science and engineering class at Penn State. You should be able to change a ratio into a percent to a mole fraction. So there might be some little stuff like that. I try not to be too ticky-tack on the exam, but I will ask you a straight up concept, and I will expect that you're able to take one step to the answer. That's called making the transition from lower division courses to upper division courses, which is what we're doing right now. Other questions? Yes. There is no in-class meeting on Wednesday. You get that time to take the exam. Now, this room will be empty. I won't be here. You can bring your laptop, and if you need a quiet place, you could do it in here if you want. Otherwise, you could do it in the library, do it in the, wherever your good place is, but there is no in-person class on Wednesday. And also, I will not answer questions or emails on Wednesday. Got plenty of office hours. In fact, here they are. Well, there's the exam format. Where the heck are the office hours? Oh, there we are. Here are the office hours. So this afternoon, tomorrow afternoon, and tomorrow night. And so you need to ask questions during this time. After 8:30 tomorrow night, I'm probably going to be pretty unavailable. And so get your studying done early. I've had good attendance during office hours, and so other people have been able to access them. If you're really caught out and want to make an appointment, I'm happy to make an appointment today or tomorrow, not Wednesday. If you have a massive problem with Canvas on Wednesday, you can email me and tell me about it. I just might not respond. Now, if 30 of you email me on Wednesday and say there's something wrong with Canvas, I'll know something is up, right? There's 100 people taking the exam on Wednesday. If one person has a problem, that might be a local issue, but if 20 people have problems, Canvas is having an issue, and we'll figure that out. Don't worry about it. But, you know, make sure that you're prepared, make sure you're ready, make sure you have a couple pencils, your calculator, the equation sheet printed, and, you know, you just want to find like an hour and a half, hour and 45 minutes of quiet place to do this exam. Other questions? Yes.
When will the solutions to the second homework be posted?
They're up.
They're up.
Check Canvas.
From today.
They're posted.
Oh,
Other questions? All right. So these are the topics, and we've covered a lot of this. Well, we've covered it all, I think. You know, TG, TM, thermosets, thermoplastics, definitions. Could be some conceptual questions in there because we haven't done a lot of calculations on TG and TM. We just talked about this, different ways of M0, what it means, M0 copolymer. Know your chemical structures. That's really important. I'm going to expect that you're like polyester. I know exactly what that is. And so that will make your answers come quicker if you're really up with chemistry, have your flashcards. Different ways to make step growth polymers. You know what degree of polymerization is, and of course we have XN and X bar W. They mean slightly different things because they relate to different parts of the molecular weight distribution. How to calculate molecular weights and dispersity, what all those things mean. Carruthers equation, R and P, you've had a lot of practice on that. Offset stoichiometry. And the one thing we haven't had a lot of practice on is statistical theory of polymerization, but I'm going to cover it again today in like the last 15 or 20 minutes to make sure we're all on the same page. The questions are asked in a really straightforward way. And believe me, you'll know when I ask this type of question just by the language that I use. And you have the equations. And so it's just a matter of really knowing what an XMER is. And remember, an XMER, we're talking about N, or degree of polymerization, average degree of polymerization. And so this is a way to think about an XMER equals 1 is a monomer, etc. So that's a way to decode when I ask you about an XMER, how to get that number. And we'll cover it again today because I want to make sure to give that full shift. Okay. Other questions? So don't forget about the stuff that we talked about at the very first lecture or two. Since this exam covers every lecture we've had so far, you know, remember what a thermoset is, remember what a thermoplastic is, remember what an elastomer is, right? We haven't done lots of calculations on these, so this is where the conceptual questions might come from. You know, we talked a lot about addition polymerization and condensation polymerizations, what those mean, how to recognize what's what, how to figure out your way around these types of polymerizations. And then we talked a lot about, where's our comparison? Our comparison between the two, right? So we spent a lot of our time talking about Carruthers equation, which is a chain growth mechanism. And so when you see those types of polymers, that gives you a hint that we're probably talking about Carruthers. As far as we know, for step growth polymerization, we just have this rapid increase in molecular weight, or this is analogous to XN, right? They mean exactly the same thing if we know what the polymer is. And we have extent of reaction also called conversion, down on the x-axis from 0 to 1. So we don't have an equation yet for step growth polymers. We might get to it, or you'll get to it in your advanced classes. And you know that Carruthers equation is the shape of this curve right here. X bar n, 1 over 1 minus p. Yes?
Two things. First of all, for the xn equation, I thought we made a different, had another equation, which like the 1 minus rn or something like that, over 1 minus.
Oh yeah, that's the extended Carruthers equation. So remember that, let me find my Carruthers equation. Remember this Carruthers equation, this x bar n equals, what does this equal if r is 1?
The actual equation.
1 over 1 minus p. Yeah, I just have 1 over 1 minus p memorized because I usually think about r equals 1, but when r equals 1, you should know which equation to use when and why you're doing it. Yes.
Yeah, no, for poly addition, well, does that just just in regard to for poly addition, is that just in regards to like one monomer, or can it be like a monomer plus a monomer for poly addition?
Yeah, so for addition reactions, remember we talked about polyurethanes and polyureas. Those are two different monomers. And since addition polymerization is step growth polymerization, if we make a copolymer, right, these are addition polymers right here, or polyaddition, and there's two different monomers in there. So remember, polyurethanes and polyureas are weird. They're mostly, they follow step growth rules. They follow step growth rules for M0. They follow step growth rules for Carruthers. They just look chemically like an addition polymer because there's no small molecule byproduct. So you could treat polyureas and polyurethanes as addition polymers, except when you draw the chemical structure, you just got to get the hydrogen all the way over to the other nitrogen on the isocyanate. Other questions? Yes.
So we could say polyaddition is whenever there is no byproduct.
Yes, that's a good one. Yeah, there's no byproduct, but you know, you want to make sure to know the exceptions. Yeah. All right. Memorize these. Memorize them. Memorize them. Know how to do the polymers forwards and backwards. It will make your life a lot easier. It will cut your exam time by 50% if you could just write these down and know how to make all these polymers. I guarantee you. If you're struggling with the organic chemistry, it's really hard to make that up on the exam, right? You know, it's really hard to figure that out. So the easiest way to do this is just to memorize these things. You have to have some common language and some common vocabulary for polymers. This is it. Just like we had to memorize our times tables when we were learning math. You don't have to think about what 9 times 9 is. You know it. You shouldn't have to think about how to make these polymers, or you should be able to recall them in 10, 20 seconds. All right. You can get out your clickers because I want to see who comes to the review session before the exam. That has a strong bearing on your exam grade, by the way. All right, we are, where the heck is the clicker thing? Hold on. Oh, there we go. One sec, it's not on yet. Okay, we are CD, and since I have a little extra time on Wednesday, because I'm just going to be making sure that Canvas goes smoothly, I will post your clicker grades. We'll sort it out if there's something weird happening with your clicker, so don't worry about it. Just keep doing what you're doing. All right. Using the bank of monomers below, which monomer would undergo an RA2 type polymerization? Not RAB, RA2. There's only one type of RA2 polymerization that we studied. It's the weird one. We just need to figure out which monomer makes a polyether. Yes. We'll talk about that in a second. Yeah. All right, we're above 50. That's looking pretty good. Oh, we're getting up there. This might be a record today. All right. Okay, click in your final answer. Oh, I didn't stop this, I guess. Oh, jeez. Okay, and the answer is 5. Because we know that this is an alcohol, this is an alcohol, and the only R A2 polymerizations that we studied were condensation of alcohols to form polyethers. Now the question was, when we have RAB or RA2 plus RB2, we need 2 different functional groups for these, right? We need an A and a B functional group. And so, we talk about RA2 polymerization, period. There is nothing called an RB2 polymerization only. We just use A. Yeah. Okay. You should know what all of these other monomers are, not their names, but how to use them. And there's a lot of polymers that you can make out of these monomers, right? Just like on the practice exam. So those should look all really familiar. You'd be like, okay, I take 1 and 2 and I make a network polyurea from that. Or number 3 is an RAB monomer that makes polyester. I get that, right? Acid chloride, I can react that probably with the amine, right? Because I know acid chlorides and amines, I'm going to make a network or branched polyamide. What about these 2? What about 3 plus 4? What do I get? Do I get a polymer with 3 plus 4? No, I don't. Because the diacid chloride or the acid chloride doesn't react with the carboxylic acid, right? That's not a reaction that we've studied. And so the DF of monomer 3, if I'm going to react it with the acid chloride, is only 1, right? So make sure that you are savvy about not making up reactions that don't lead to these groups. Okay. Let's keep going. Another clicker question. Reacting monomers 1 and 2 would give, well, I'm glad I didn't draw that out. What polymer do I get when I react 1 and 2? All right, we got 57 last time, so I'm expecting 57 again. All right, getting closer. And so when I react an amine with an isocyanate, I get a polyurea. Lots of nitrogens in there. That's how I tell the difference. If I reacted an isocyanate to, let me stop this, thank you. If I reacted 2 plus, let's say 5, what do I get with 2 plus 5? Yeah, you get a polyurethane. And actually 2 plus 5, is that branched or is that linear? What's the skeletal structure of 2 plus 5? Linear. What's the skeletal structure of C? Branched or cross-linked. They'll lead to the same thing after a while. It starts off as branched and then eventually gets cross-linked. But it'll be clear what the answer is if I ask you something like that. Yes?
So when you say branched or crossing, so we had thermoplastics, I believe.
Yes.
And then thermosets. So it says that the thermosets are crossing, but thermoplastics are branched, and now we say branched or crossing. So I was confused about that.
Yeah, this is a good point. So crosslinks are thermosets for sure. End of story. You need crosslinks to have thermosets. Now, what I don't tell you is that if we're making a polymer with DF higher than 2, is it branched or is it crosslinked? It actually depends on P. You'll study that in future classes, but I'm not gonna, but all thermoplastics are either linear or a branch. So we make the distinction here and we say we have a branch polymer, it's a thermoplastic. We have a cross-linked polymer, it's a thermoset. The reason that I say branched or cross-linked is basically because we don't know P. And so it's just important to state both of them, and it depends on what P is. Yeah. Let's see, do we have any other good ones here? No, okay, we have Carruthers equation. Okay, let's run through this one as our last clicker question. Then we're going to talk about statistical Carruthers theory here in a second. So you want to make a polymer with Mn of 15,000 grams per mole. Okay, the polymer length, yes. Oh, sorry. Yeah, now you can't read anything. Yeah, I got you. Let me put it down here. All right. So right off the bat, molecular weight or Mn is 15,000 grams per mole. Okay. And have the ability to achieve a full extent of reaction. Full extent of reaction, full conversion. I did you a favor and I said that that's P approaching 1. I don't have to tell you that. If I tell you equal stoichiometry, that means that R equals 1. So there will either be some word hints or some gimmies like this on the exam. But I could ask you both ways. I don't have to tell you that P is 1 if I tell you full extent of reaction. If we begin with 1 mole of 1,4-butane diol, how many moles of adipic acid do you need if it is the limiting reagent? Question, mole, limiting. So here's the Carruthers equation right here. There's no guarantee that I'm going to write the equation right next to the exam. You might have to go find it on your equation sheet. But what is this question really asking you? What am I asking you for? What don't we know in Carruthers equation? R. And R, the definition of R is what? NB. And that's the moles of functional group, not the moles of monomer. Okay. So which don't we know? NA or NB? Which one are we looking for actually? NA, that's right, because it's limiting. So what's NB? 2 times DF equals 2 and B equals 2. Okay. So I still don't know R and I still don't know NA. And so how do I figure out R? What do I need? I need to figure out XN. So I need to figure out the polymer. Right? I need to figure out the repeat unit structure and how many repeat units are in an Mn 15,000 grams per mole polymer. So we draw the repeat unit. So this, of course, is going to make a polyester. Here's my repeat unit right here. And then the tricky part again, as we started the class with, find M0. So 200 grams per mole is the stuff between the parentheses. And since there's 2 monomers in that repeat unit, M0 is 100 grams per mole. That is the hard part of this question. And since M0 is 100 grams per mole, I've got this equation right here, which tells me if I divide the chain molecular weight by the M0, I get my X bar n of 150 and I can solve for R, et cetera, et cetera. Yes,
So instead of drawing the repeat unit, since we know that it's gonna form a polyester, you know, the byproduct would be two water. So we could just sum up the two and minus two water.
sure. If you want to try and take the shortcut, go for it. But you can't lose if you draw out the polymer structure and figure out what's between the parentheses. If you start trying to subtract byproducts, good luck. Do it this way. It's easier. Yes.
So the 200 grams per mole goes with the butane.
Nope. That's all the stuff between here. So this whole thing is 200 grams per mole.
So we would have to draw the repeat unit.
Yes.
Yes.
If we're talking polymers, draw out the repeat unit, think about it, make sure the chemical structure is right. Write out all the carbons, write out all the hydrogens, right? Because there's hydrogens. Whoops. If I can get rid of that. There's all kinds of hydrogens on here, right? Make sure you get all those. It's tricky. This is getting there in terms of a lot of information that you have to synthesize, but you should be able to make the polymer and figure out what the M0 is. Yes.
So when you divide by two, don't we do that if you're like combining monomers with one polymer? Or, if there's two.
It is the number of monomers in the repeat unit. That's the definition. So for all the examples we've done for step growth, where it's RA2 plus RB2, it's two monomers going in, but it doesn't have to be two monomers, right?
So if there was three, you divide by two.
Sure, we haven't done any examples of that, but yeah, it'd be three. And in addition polymers, it's one, right? So we just divide by one. Yes.
I think my biggest like sticking point with that is like what we were just talking about is I see MN, the 15,000 grams per mole, as the overall chain. So whenever I see that whole repeat unit, I think, okay, that 200 grams per mole is like part of that. So that way we won't have to divide by two. So that's
Yes,
my sticking point.
that is a sticking point, and this is how you get P correctly. So it's not based on what we think is reasonable. It's based on the math working out to get P correct. Because remember, what's the definition of P? Functional groups that that are reacted versus number we start with. And so because of that, because of the definition of P, that's actually why you divide by two. But you're much better off memorizing how you get M0 for different types of polymers, copolymers, two monomer step growth polymers, things like that. So there's a real reason. I mean, we're just not dividing by two just because, and just because Carruthers told us. It's to get accurate P. So if you don't divide by two, your P is going to be wrong. Yeah, it's a tricky thing. Yeah. Yes.
Could we do this problem if we weren't in P?
No, because then you'd have one equation and two unknowns. Yeah, I mean, I promise you that you won't have to solve a system of equations for two unknown variables. So I will give you information that's basically going to boil down to one thing that you don't know. Yes.
So when you're multiplying by the two on the previous slide,
Yeah.
why would you not do it for both the numerator and denominator? Because aren't there two functions both of them? Because you're multiplying the NA by two.
I'm not multiplying NA times two or NB times two. NA is the number of functional groups. NB is the number of functional groups. I have 1 mole of butanediol, so NB is 2. 1 mole times 2. I'm not multiplying NA or NB by 2. I'm getting NA and NB by how many moles of the monomer I have when each is DF2. That is a different thing. Remember, number of moles of monomer versus NA is different because the DF is in there. And that's very tricky because I won't generally ask you about how many moles of functional group do I need, and B, I'll say how many moles of monomer do I need. Remember that. That's tricky. Yes.
Does the adipic acid have the DF of 2?
What do you think it has?
I would say 2.
Yeah. It's going to make linear polymer, right? Adipic acid has 2 carboxylic acids on it. You should be able to look at the monomer you need to know what the chemistry is, right? So if I want to make a polyurethane, adipic acid has a DF of 0 because these functional groups don't go into polyurethane, right? And so you need to know what the polymer is, and then you can look at the monomer, and by inspection, you should be able to get it because you know what chemistries go into making these things, right? So if I just give you a monomer and I say, what's the DF? You should say, well, what polymer are you trying to make? Yes.
So just kind of like you say, you need to know the actual polymer in order to actually get functionality.
Yeah. I mean, I might give you a monomer and say, what polymer does this make? But you only have a choice of one monomer. So you're like, okay, does that make a polymer that I know about or not, right? Don't invent any new organic chemistry on the exam. This is what you need to know. You won't have to figure out anything that we haven't talked about. Other questions? All right, we are going right to the end because we could talk about statistical theory of Carruthers, which is really interesting. And so, all right, you can do it. Come on. There we go. All right. So this is called the generalized Carruthers equation, right? We're not talking about statistics in this one at all. And so when we had the statistical theory of Carruthers, which is a theory based on the probability of monomers in the chain. So if you look at those notes, it was the probability of monomer versus the probability of having a dimer versus the probability of having a trimer as this polymerization is proceeding. And if you put those probabilities together, I'm not going to make you derive this equation, but you should know how to use this equation for sure. So the probability of finding a sequence of X units, a dimer, a trimer, a 50mer, a 1mer. And so you know what X is because we talked about Xmer. And P in this equation is the P that you know and love. It's the degree of conversion. Because when the degree of conversion is 0, this will reduce down and you get the probability of finding a monomer is 1, right? Because that's all monomers when P is 0. All right. We're not going to worry too much about the mole fraction of Xmer. You can think about that if you want. But we do care a lot about the weight fraction of Xmer, because if we're making polymers, we're going to use masses of stuff or weights of stuff. And so we'd really like to know how much monomer is left over. We'd really like to know the weight fraction of 100 mers, right? Because that tells us about the molecular weight distribution. And so this equation is really important. And this equation is really important. They're both on your equation sheet. I think this one's actually on your equation sheet too, but I'm probably not going to ask you a lot about that because we don't talk that much about the starting number of moles and the moles of an Xmer. So the way these questions go, and we talked about this last time, is that we're polymerizing the below monomers, 1 mole of each, R equals 1. Remember, there's no R's in this equation, so probably should be R equals 1. When you stop the reaction, there are 0.1 moles of acid chloride groups left. What weight fraction of monomer do you have left? Weight fraction is this equation, monomer, X equals 1. And so what's the one variable that we don't know in that equation? P, right? P equals number functional groups reacted over starting functional groups. If you write down the definition that you can't lose, right? How many functional groups do we start with? Two moles, right? Because we have 1 mole of monomer, so we get 2 moles of functional groups. And then we have 0.1 moles of acid chloride groups left, which means how many groups reacted? 2. If I only have, if I have 0.1 at the end and I started with 2, how many reacted? 1.9 equals P. And so if I run that in, I can't remember what I get. So I have 1.9 over 2 is 0.95. I sub that in and I get 0.0025. So that is my weight fraction of monomers left. It's not a lot, it's a small number. We're dealing with P, but this is the way that I'll ask these types of questions on statistical. You need to know it exists. You need to know how to use the equations, but the questions are going to be asked just like this. Yes. How do I know? That's a very good question. How do I know that X equals 1 in this? What's the key word? Weight fraction of monomers. I could ask you, what's the weight fraction of trimers? X equals 3. Weight fraction of 100 mers? X equals 100. So make sure you're able to decode what X is based on the information I give you. Yes.
So, like you said earlier, if R is not given explicitly, you can always assume it's equal.
That's right. So unless I give you some information about how many moles of this or that, or if I give you some coded language on offset stoichiometry, or I could tell you that it's a stoichiometric reaction, I will be telling you about R.
Well,
Yeah.
We also think about it in sense like now, we're given 1 mole each, and we can find NA, which is 1 mole, 1 mole by NA, and B, which is 1 mole, and you know.
Sure. Yeah. 1 mole of each. That, I mean, that tells you that R is 1. Yeah. So you could go all the way and do the math if you want. Yes. Yes.
How come it says number of functional groups and not moles of functional groups? That's when we end up putting the number of moles.
Well, what's the difference between number and moles? Anyone know?
Mole is just a stand-in for a really large number of molecules.
That's right, because of Avogadro's number. So number and moles are the same. It's the same thing. There's just, you know, whether you want 6 times 10 to the 23rd in there or not, right? Yeah. So it's a lot easier to talk moles some cases. Yeah. Yeah. All right. So I want to show you 2 more slides in the last few minutes, and I'll stay and answer questions, so don't worry about that. So when you plot out these most probable distributions, it looks really interesting because you start to get, oh, as I go as a function of P, so this is increasing conversion, and you can see the legend up here. I get more and more of this high XN stuff. And my molecular weight distribution changes because these are in essence molecular weight distributions, right? The amount of something on the y-axis times the x-axis, which is degree of polymerization. And so I can take those distributions, and you don't need to worry about this too much, but we can express MW and MN as a function of P for step growth. And this is a shortcut on the homework problem that I forgot to talk about on Friday. I emailed you all through Canvas and brought this to your attention because I had forgotten about it. But if you know something about the degree of conversion, you know about the ratio of MW and MN, and this is dispersity. So at P equals 1, the theoretical dispersity for step growth polymers is 2. And the dispersity for step growth polymers goes between 1 and 2. That's it. And so these equations are easy to use. They'll be on your exam sheet, but make sure that you know how to use these when appropriate. Yes.
So is there a difference between the italicized P and just regular P?
Nope. Nope.
When I was doing the homework, I found that when using the perspective way after formats to find, I think like the actual MW was different from the value of after I used it. So is there some sort of rounding error of that, or?
You used what? Hold on, we're not done yet. You use what?
I used the I first did the MW equals MO, the times 1 plus the other 1 minus P.
Yeah.
I got the value for the MW, which I use for. Is there?
Oh, yeah. If you know the dispersity, you need to use that. because the dispersity is actually a direct measure of MW over MN. If you don't know the dispersity, this is the theoretical equation if you know P. But if you know MN and you know the dispersity, don't use this equation because the dispersity is an experimental number that you measure. This is theory. And so even though this looks tempting, if I give you MN or if I give you the dispersity in another form, it'll be obvious. I mean, the homework is a multi-part question. I'm not going to ask you something that complicated on the multiple choice exam because there's a lot of pieces to that. But make sure you have some recognition of when to use what. All right, I'll see you in office hours, and I'm happy to answer any questions. Thank you.